Okay, so looking at question 8 here, we see we have two cables, 35 meters long. We're told each cable has a mass of 4.8 kilograms per meter. Find the weight of a 35 meter length of one cable. So we know that weight equals mass times gravity. But if we actually want the mass of the cable, we've got here the mass per unit length multiplied by the length of the cable. The lengths will cancel to give us the mass, multiplied by gravity. So the mass per unit length is 4.8, the length is 35, gravity is 9.81. And so when we calculate these together, we get 16,480.8 newtons. We should round this to two significant figures, which is 16,000 newtons. Two significant figures because the numbers in the question are given to two significant figures. Okay, the cables would break if the crane attempted to lift a load of 1.5 times 10 to the 6 newtons or more. Find the breaking stress of one cable. Well, we're only asking about one cable, so we need to think about how much weight would one cable be carrying, and it would be this number divided by 2. So this is 7.5 times 10 to the 5 newtons. That's the force that's in each cable. So stress equals the force per unit area. Now, we're asked about the breaking stress, but really that's the breaking force. So as you know, we could add, if we want, the breaking stress and the breaking force, but we don't actually need to. So what force would break it? Well, it would be 7.5 times 10 to the 5 as the force that would break it. The area is given as 6.2 times 10 to the minus 4. Just check the units, it all looks good. Newtons here, meters squared here. So we're in the right units to get pascals. So that number divided by the area gives me, a really horrible number. I'm going to use the ENG button on my calculator to get that to 1.2 times 10 to the 9 pascals. That's already two significant figures, so I'm happy with that as it is. Next question. When the crane supports a load, each cable experiences a stress of 400 megapascals. Cable obeys Hooke's law, ignore the weight of the cable. So find the weight of the load. So let's look at what we've got. We've got stress. Now, we've got one cable only. And we've got the Young modulus. Okay, so let's find out then. So stress is force over area. We want to know the force. So force equals stress times area. Now, how we go about this is there's a few different ways, but is this right? Yeah, I think so. Yeah, cool. 400 times 10 to the 6. Remember, this is only for one cable, multiplied by the area. So the area was given in the previous question, 6.2 times 10 to the minus 4. So 400 times 10 to the 6 times 6.2 times 10 to the minus 4 gives me 248,000 newtons. But that's only on one cable, so we need to multiply by 2 to find 496,000 newtons shared between the two cables. Now, two significant figures here actually takes us to 500,000 newtons. Okay, the unstretched length of each cable is 35 meters. Find the extension when it's supporting the load. So there's quite a lot of information here, but I think we can probably get there. So I'm going to write out y equals flee. Now, apologies if you haven't seen it like this before, but it's the way I was taught it in school, and it works really, really well. Y is the Young modulus, not using the symbol capital E, which AQA uses, and E is the extension, again, not using delta L. I find this the easiest way to remember it. Let's see if we can rearrange for extension. So this would be FL over YA. And then let's collect things and see how much we know. So one cable, let's do everything about one cable here. So the force in one cable is 248,000 newtons. The unstretched length is 35 meters. The Young modulus is 2.1 times 10 to the 11. And the area, which keeps cropping up, is 6.2 times 10 to the minus 4. So bring all of that together. Let's calculate 248,000 times 35 over 2.1 times 10 to the 11 times 6.2 times 10 to the minus 4. And I get an answer of 0.06 recurring. Two significant figures. I'm going to give that as 0.067 meters. Calculate the combined stiffness constant K for the two cables. So F equals K times E. So this is spring constant or stiffness constant times extension. So K equals F over E. Now we want for both cables, so we know that the total force for the both cables is this 496,000. 496,000. And the extension, well, the extension of one cable is 0.067, but the cables are next to each other, so they both extend by the same amount. So I'm going to go with my 0.06 recurring, type into my calculator, and we're going to get the answer of 744,000 newtons per meter, or is that the easiest way to write it? 7.4 times 10 to the 6. 7.4 times 10 to the 6. That's a pretty big number. On one hand, I'm thinking that seems really big. On the other hand, it seems pretty reasonable. I haven't checked the mark scheme at this moment, so I'm going to assume that's right for now. Watch this space for me to check the mark scheme and spot something I've done wrong. Last one, the total energy stored. Well, energy equals half KE squared. So we've got half times the stiffness constant that we just calculated, multiplied by the extension, 0.06 recurring squared. And hopefully we're going to get the right answer here. It's me furiously typing sixes into my calculator to recreate that recurring. And I get 16,533 joules, which I guess, again, to two significant figures, 17,000, not very nice. But I guess we'll have to go with it, 17,000 joules as the final answer.